and then that's a very intimate type of seminar. So if you ask anything during the talk, okay? So yeah, Jong-Hyun is now in Helsinki University. He was a student of Stefanos Koper in Sogan University. So he went to Helsinki for PhD. His advisor is Oleg Lebedev. And he's gonna move to Orsay in a month. So hopefully, yeah, he can visit us. Oh, yeah. 줌 없어요? 줌? Okay.
It's on Zoom, right?
Anyway, yeah.
Anyway,
Okay, so please.
thank you. So, first of all, I'd like to thank Jong, Thomas, Jong-Hyun, and Soo-Kim for their hospitality. My name is Jong-Hyun Yoon, 54J. I'm a PhD student at the University of Helsinki. So today, I'd like to talk about what I've studied and what I'm working on in Helsinki. So the title of this talk is Dark Matter Production During Preheating. So preheating might sound unfamiliar to you, so we are going to study basics of preheating and why it is important. And we are going to study different production mechanisms of dark matter during preheating. So contents are the following. We are going to have a brief intro, and we will learn about basics of preheating, and we try to apply such preheating effects to study different production mechanisms of dark matter in terms of scalar fields, including inflaton hits and scalar dark matter. So this talk contains 4 papers, but the first 3 work is closely related to preheating effects. So we are going to focus on the first 3 papers. And then I'll mention the last one briefly, and then we will sum up the main points at the end. So the nature of dark matter remains an outstanding mystery of modern physics, and non-detection of dark matter signal in experiments implied that dark matter interaction might be small or weak, and it motivated us to study the origin and emergence of dark matter in the early universe. And on the other hand, the idea of cosine inflation came out as a solution to some problems of the conventional Big Bang cosmology, and it is realized that
Recording in progress.
it's okay. It was realized that the dynamics of this inflation can be understood in terms of the dynamics can be understood in terms of a real scalar field. So how about trying to explain dark matter production in terms of the inflaton decay?
So can you remind us what happened in the year of 1933 and 1975?
It was a time when Jacobi studied dark matter kind of seriously.
Okay.
And then
79?
this is a time when people try to come up with the idea to explain horizon and flatness problem of the conventional Big Bang theory. So
okay, so the first of the inflation theory.
Yeah. So there are many different mechanisms of particle production, but we are going to focus on non-thermal production of dark matter. And this is an equation of motion for a scalar field in momentum space in general. And the number density or occupation number is preserved by the adiabaticity condition. In other words, if you break the adiabaticity condition, you will generate particle. So there are many different ways to break this condition, but people found that the inflaton oscillation after inflation can also break this adiabaticity, and this relevant regime or time period is called preheating.
So, so prime is the time derivative?
Yes.
It's the usual time or
It's physical.
physical time?
Yes.
And A is a scale factor. Cosine is. So what is cosine?
It corresponds to non-minimal coupling to gravity of high field. So this is a kind of introductory part. We're gonna.
Chi is scalar or?
It's a scalar field.
Okay, scalar.
And this is an overview of the early universe. So we believe that our universe was formed a hot dense plasma in the initial time. And by the process called reheating, and people found that reheating can be intense because of the oscillation of the inflaton with a large amplitude, and this phenomenon is called preheating. So it means that even tiny interaction can lead to efficient particle creation during preheating.
What is the difference between reheating and preheating?
Reheating is generally understood to mean any process to reach the thermal universe, but people found that this effect can be intense right after inflation, because right after inflation, the inflaton background starts to oscillate around the minimum, and it has a large amplitude. So we are going to learn about how it works. So preheating is a composite word of pre and reheating. It means the intense particle creation right after inflation. And we found that it involves nonlinear and non-perturbative effects, collective effects such as resonances, back reaction, and rescattering. So to account for such effects, we have to perform lattice simulations. Now we're going to study basics of preheating with a simple example. So we are going to assume Cortic inflaton potential, and we can solve equation of motion for inflaton background. And this is equation of motion for the inflaton background, and with the help of mathematics, we can find the solution of this equation, and the solution is known as Jacobi cosine function, which is quite similar to cosine function. And the amplitude gets redshifted by the scale factor. So on the right is the example figure of the inflaton background. It's oscillating, and the amplitude is also decreasing. So with that solution, we can solve equation of motion for the produced particle. That can be any scalar field in this example, but it has to interact with the inflaton with a Cortic
Sorry,
coupling.
can you go back?
Go back.
Previous slide. So phi is inflaton gauge.
Yes.
Then you have the equation of motion. Psi is we define field.
Yes.
Okay, so you should mass list.
Yeah. In this example, in this simple example.
You just have phi to the fourth potential. And then time dependence phi goes like Okay, so Cn is the function, I mean, that's the function you do, yeah.
Yeah, it's called Jacobi cosine.
Jacobi cosine integrals. Okay. So phi zero is initial amplitude. Okay, thanks.
So please feel free to interrupt me whenever you have a question. So with that solution, we can solve the equation of motion for the produced particle that can be any scalar field. We should interact with the inflaton with the vertical coupling. Then you will find this kind of equation, and this belongs to so-called Lamé equation. So the characteristics of this equation can be determined by two parameters. One is rescaled comoving momentum, and the ratio of the interaction to lambda phi, which is the coefficient of the inflaton potential. So you need the so-called Lamé instability chart. So, which means when a certain mode is inside this unstable band, the solution will grow exponentially. This explains how the resonant particle production can occur.
So here kappa is kind of rescale the momentum of SP.
Yes.
So what you have on the x-axis?
X-axis represent Q parameter. So
Q parameter, which is okay. That's better.
Okay.
So so you draw red line. So when Q is certain value,
Okay.
you have this blue region. So what does that mean?
So in a realistic case, Q is fixed because lambda phi f and lambda phi is fixed. So you can draw kind of possible momentum modes like this way because Q is fixed, but momentum can be any number, right? So you can draw this line, and you will see regions here belongs to unstable band. So the solution will grow exponentially.
X. I mean.
Yes.
Okay. So x gives like exponential to the x, to the x, or to the whatever.
Yeah, it's the time also.
Okay, time.
Otherwise, it will just oscillate. There's no particle generation.
S is a scalar field coupling to the inflaton field.
Yes.
So amplitude of S grows exponentially once the condition meets. Okay. Okay.
So you want to see numerical behavior of the solution, right? So on the right, you can see the number density of S field, and you can see it's growing exponentially. Actually, this generation has to do with the violation of adiabaticity. So this period corresponds to the period of inflaton background.
So you just the background is fixed. The inflaton background is there.
Yeah, that's a good point. Yes.
And then, so probably if it grows very fast, then there could be some important back reaction.
Wow. Yeah, that's what we are going to
Okay.
study in our next slide. So we define the first phase, linear state, that we can assume the inflaton background is the dominant one. But around the end of resonance, this assumption is not true. It's no longer true because the interaction can be more significant than the inflaton background term. So we cannot assume this inflaton dominance. So you cannot solve the equation of motion for the inflaton background. We cannot obtain the Jacobi cosine solution of the Jacobi cosine function. So around this time, back reaction and rescattering set in, which means produced particles can back react, and different mode with different momentum mode can scatter each other. So it's really difficult to analyze the system analytically. That's why we have to rely on outcome of lattice simulation. And then the system will enter into the second phase, which is nonlinear. So the particle interaction is still going on. It's not as explosive as before, but still they are active. So at strong coupling regime, the system will enter into energetically stable state. So we call this state quasi-equilibrium. So when the interaction is large enough, you will see this kind of energy fraction between inflaton and the other scalar field. This represents energy fraction of each field. And another important feature of the quantic preheating system is that phi to the first serves as an interaction term itself, which means without any interaction with other field, it can the inflaton background can be broken by this self-interaction. So you can work out the equation of motion like this way. You can expand phi in terms of the average value plus fluctuation. Then you want to quantize this fluctuation by canonical way. Then you will obtain this kind of equation, which is the same as the Lamé equation, but Q parameter is fixed. So you have kind of effective Q parameter, which is fixed to be 3. Since in this case you don't have explicit interaction with other field, but only self-interaction. So you can draw orange lines that represent possible momenta modes. So Q is fixed at 3. And you see there's always a region where the modes are growing exponentially, which means you will always have this kind of exponential growth of inflaton quanta. Okay, so the left figure represents the decay of inflaton background, as you can see. So it's fixed in conformal unit, but at some point it starts decreasing because of the self-interaction. So the energy of this inflaton background will be converted to the energy of inflaton fluctuation. So we can do the same thing for the quadratic case. So the procedure should be the same as the previous one, but you will obtain different solution of inflaton background, and you will have different equation motion for the produced particle. And in this case, this equation is called Matthew equation. So we can analyze the characteristics of this equation as we did before, but the difference is that the system is not conformal, which means these Matthew parameters are varying over time, whereas in the quartic system, those parameters are fixed. So these are varying, and the minimum of AK is fixed to be 2Q, since this term is always non-negative. And so you can draw this kind of red line represent AK is equal to 2Q. So in a realistic case, you can fix Q and draw this kind of possible momentum modes. And you can find that A and Q are decreasing over time. So they are going to move to the origin in the end. And these shaded regions represent stable mode. So any mode inside this stable region will not grow exponentially. They just oscillate. So it's boring. So you will see resonant event outside this shaded region. It also means that you can find the end of, you can predict the end of preheating when Q is around this point, since all the momentum mode will go to this stable band. So there's no such exponential growth anymore. Because of varying A and Q, the occupation number can increase and decrease. So this behavior is called stochastic. And the equation of state is also evolving in the quadratic system, whereas quadratic system, in the quadratic system, equation of state is fixed to be that of relativistic one, which is one third. In quadratic system, equation of state is fixed to be 0, but it can grow depending on the interaction strength between inflaton and scalar field. As I said before, we can predict the end of resonance by looking at this chart. So at recoupling region, preheating is expected to end around this region. So in other words, when Q is around 1, you expect the end of preheating. But at strong coupling region, that analysis breaks down because rapid interaction can break the inflaton background. So this analysis will not work anymore because the strong interaction can break the linear analysis all the way. So instead, when the interaction is strong enough, you will see such kind of energetically stable state that we call quasi-equilibrium. So the total energy of the system at some point is shared by each field component, and then they grow by the scaling law. Okay, this is outline of the both preheating models, and one of the important difference is the self-interaction in the quantic system, and the quantic system is always conformal and relativistic. But they both have non-linear and non-perturbative effects that we should consider. So to account for such effects, we perform vector simulation.
So does the same phenomenon occurs for fermions compared to inflaton?
Not as significant as scalar case, because it occurs due to the Bose-Einstein condensation.
Due to Bose-Einstein condensation. But in your formula, I don't see any Bose-Einstein distribution function or something like that.
we believe in Fermionian case, um, I think it has to do with Pauli exclusive principle. So you cannot take.
Okay,
for-
so yeah,
for-
only given momentum mode grows, so there is a limit.
So what lattice simulation too?
So you said this equation of state is 1/3 for phi to 4
Yes.
inflation. Did you have formula to show
Uh,
how? So this S field, can you show the equation of motion for S field?
that's good. In this one.
No, previous. Phi to 4. Okay, S field. Probably table. Okay, so yeah, X is rescaled S field.
Yes.
So particular momentum mode grows. It has a huge occupation number, and then you get some energy density, and then pressure is 1/3. I mean, how can you know the pressure? I mean, this is omega is 1/3.
I mean, relativity case in the. Well, I mean, both particles are relativistic, so it's kind of textbook material. So if you have relativistic particle, you will have equation motion, equation of state.
Oh,
One
again, that's because why relativistic?
It's effective massless.
Effectively mass.
And you can also work
So
out.
meaning that the quantity inside the parenthesis vanishes? And they have kappa square plus something. So that looks like a mass term, right?
Mhm.
Yeah, anyway, this mode is massless, you say.
Yeah.
Yeah, that's why you can grow. Okay.
Okay, so we need to perform lattice simulations, and what lattice simulation do for us is to solve equation motion at spatial point explicitly. So it means we don't need to rely on the assumption that we made in the inflaton dominance. So we write equation motion including this vector. And the outcome of lattice simulations consists of two sets of parameters. One set includes field values, energies, and so on that are obtained average over space. And the second set contains power spectra and occupation number or frequency that has dependence on momentum. So now we are ready to make use of the outcome of lattice simulations to study different dark matter scenario. So first we need the model, and since the time scale of reheating is huge compared to the one of preheating, so we need to extrapolate the outcome of simulation to reheating. And we are also going to assume the instantaneous reheating by inflaton decay to heat. So this is the typical assumption you can find in the literature. So, and then we are going to impose constraint by the radical bundles of dark matter. So first, we assume a simple monomial inflaton potential, and we add quadratic quadratic interaction term between inflaton and dark matter. And you also need this term for the inflaton decay to 2 Higgs, which is essential for reheating. So, as I just said, we assume in the instantaneous reheating, it means when this interaction rate, decay rate, is comparable to the Hubble rate, you will obtain the summer universe. And we impose the constraint of the radical bundle this way. So we assume that this number is fixed after the summer universe till today.
And is number density of
Dark matter.
S. S.
Yes.
Excuse me, may I ask one thing?
Yes, please.
In the previous slide, can you have an interaction between phi and a linear interaction of phi to s? For example, phi s squared.
Yeah, that's possible. Yeah.
And do you have
So-
any reason to you don't have it now?
So actually we did it in the papers. It's just that I'm not showing in this talk because I want to focus on the preheating effects.
Okay.
That's also
I see.
possible.
Okay. But any special difference between having it or not?
So in that case, we are not going to work on preheating effects. So there's no resonant behavior during preheating. So you want to solve the Boltzmann equation by perturbative approach.
Okay, so preheating effect is less subdominant. That's what you are saying, right? When you include that linear interaction.
So if you want to focus on only linear interaction, you don't want to include the preheating effect because it can lead to tachyonic resonance, which is very efficient. So, and it's more complicated and involved to study such tachyonic events.
Okay, you are trying to simplify things by separating. Yes. Okay, thank you.
So you also need to worry about the overall sign of potential as well in that case, because this can be negative and it can make the whole potential being negative. So it's more involved, let's say.
Okay.
So S field has some mass, right? But you didn't write.
It has mass, but
MS
it's
field has-
negligible
Oh, it's negligible.
in this particular time period.
Meaning that much smaller than that particular
Yeah.
value, lambda phi.
Yeah,
Okay.
exactly.
And they are relativistic when they are both.
Yes. And it will become non-relativistic at reheating.
At reheating.
Yes.
So quickly becomes non-relativistic.
Yeah. So because it's impossible to simulate particle interaction till reheating, so we need to divide this time period into 2 steps by making use of the equation of state. As we saw before, the quadratic system will be dominated by the inflaton because the relativistic quantity scales as a to the minus 3, while relativistic one scales as a to the minus 4. So eventually, the inflaton will dominate the system.
So AC is producing non-thermally, right? This dark matter is you're producing it non-thermally.
No summary, yes.
Yeah. So I mean, if it's produced non-thermally, then how are you defining it relativistic or not? Because it doesn't have any temperature, right? If it's producing non-thermally, then it does not have any temperature. You cannot define any temperature for that. Then how do we know whether it's relativistic or not?
But still, we can see the distribution of momenta, and we can compute the energy per quanta. And if it's large enough, we can say it's relativistic. But when it becomes smaller than the bare mass, then we say it's not relativistic.
Yeah, probably he calculated dispersion relation somewhere, right? So omega k was like a k squared plus something else.
For inflaton.
That was for inflaton.
So we define this moment where the system becomes non-relativistic due to the inflaton. And then we're going to work out the outcome of lattice simulations, and we find this momenta and to obtain this kind of relation. So you can find the function for sigma phi h in terms of lattice outcome of lattice simulations and mass of the inflaton and so on. So E represents the end of preheating, end of simulation.
Sorry, what does the sigma phi h stands for?
This stands for the coefficient of the trilinear coupling.
Okay.
Up here.
Okay. Thank you. Sorry.
No problem. So we can also predict something at strong coupling, because when the interaction is sufficient strong, we expect the system to reach quasi-equilibrium at some point. So we found that this term is equivalent to the energy per quantum of the inflaton. So you can replace this fourth term with this term, and then you will arrive at this equation that doesn't have any dependence of simulation outcome. So this is the final result of this work. So as you can see, at strong coupling with the kind of behavior that doesn't have any dependence on simulation parameters, but only on mass and basis of inflaton and dark matter. This is for the quadratic case, and you can do the exactly same thing for quadratic case. And then you have this kind of picture. And it means that even tiny interaction can explain the abundance of dark matter. And you can also obtain the information about reheating, because this value can be directly converted to the reheating temperature. So this work is very generic. So you can you can choose different parameter choice, such as a method inflaton or method dark matter. So this is a kind of example parameter choice that leads to the reheating temperature, which is 50 MeV.
Some strange question. Can you take MS down to say 10 to minus 20 electron volt?
I think that's more involved because of the structure formation constraint. So we need to care about.
I mean, that's another question. I mean, that's a separate question. But in your scheme, is there no problem taking MS down to 10 to minus 10 or 10 to minus 20 eV?
So in our work, we found that the typical energy of MS is comparable to the typical energy of standard model particles, which means that it should be heavy enough. Otherwise, it's hard to explain the structure formation constraint.
Structure formation constraint.
Yes, because we don't want to have relativistic dark matter. We want to have called non-relativistic dark matter. So we want to have heavy enough dark matter. But it also
So
depends
when
on
does
the
it become
distribution.
non-relativistic? So when
So it was relativistic, but because of the expansion, it can be.
Oh, basically, okay, you mean basically this guy becomes non-relativistic when temperature drops below the mass. All right? But somehow this guy, I mean, it's related to the previous question. I mean, this guy is not in thermal equilibrium, but still relativistic. Then when does it become non-relativistic?
I think this has to do with the momentum distribution that you mentioned. So, so we need to compute the energy per quantum.
It's not perturbative decay, right? It's not a decay of inflaton to S.
Yeah.
It's a non-perturbative decay.
No,
Non-perturbative production of.
perturbative. No, it's not.
It's perturbative production.
No, it's non-perturbative.
Then how can we calculate this momentum or velocity distribution in that case?
So we need to study the outcome of simulation. So we can see the distribution. I mean, we can study the power spectra of S field. We can study the how the expansion can scale the energy per contact, and so on.
Is the typical momentum of the S particle around close to the mass scale of phi? No?
You mean the typical energy per contact is similar to each other?
I mean, yeah, typical momentum of the
yes.
S field would be, I mean, after due to the preheating, the momentum scale, typical momentum is around the mass scale, similar to the mass scale of phi instead of S field, right? Then S field is relativistic at the time of S production.
Oh yes, during preheating, yes.
Yeah, and then eventually due to redshift, it will become non-relativistic.
Oh yes, yeah. Exactly.
You are not assuming the thermal equilibrium between those two fields, right?
Sorry?
I mean, the S field is not in thermal equilibrium.
Not in thermal equilibrium.
Yeah, so its momentum is just redshifted.
Yeah, we assume so, yes.
Yeah. Then initial momentum is given in some sense provided by the initial momentum is something like inflaton mass. And then you know when this S field become non-relativistic after preheating, right?
Yes. Yeah, so you're happy with the answer.
Can you go back to this? I mean, you had this the range of kappa which can
You
So
mean
you say
the
this is that
instability
kappa
chart.
corresponds to around TeV or what? No, let's go to 5 to the 4 case. So
Something
the
like
kappa. So here the you didn't show. Okay, you didn't show. So kappa is what?
It's viscous co-moving momentum.
Is going what? Is K? Yeah. The K is the momentum.
Co-moving one, yes.
So you say K is around ms? Seems not.
No, it would be something like
M5.
M5. Yeah.
K is around M5, is that right?
Yes.
But it depends on phi 0 for the lambda phi. Why should it be M5? The kappa is around 2, 3, where this mode grows. And then it's the combination of a momentum and something else. So depending on the part of the choice, it can be any reason.
So first of all, kappa can be any number, but what I mean by M5 is the effective mass, which corresponds to this value. So typical momentum scale is comparable to
Okay,
this.
so that's M5.
Yes,
Lambda 5.
effective mass.
Okay. When you say inflaton mass 1 TeV, you mean lambda phi 0 scale?
So it's a bit complicated. So we need the bare mass of inflaton.
Okay, so
So
it's not lambda phi. I mean, during inflation phi, maybe trans-Planckian, right? And lambda very small.
Around 10 to minus 13 or something.
Yeah, 10 to minus 12, 13 or something. So the typical scale is comparable to.
Okay, so anyway, when you say it's lambda phi not squared, must be m phi squared. Is that right? That's what you say.
Sorry.
So lambda phi squared must be m phi squared.
Lambda phi.
Denominator is mass squared, right? I mean, that's just what you said.
So I mean.
So later you take m phi is 1 TeV. So the denominator is basically.
So okay. So that one is something that we need in the Lagrangian, but when we study preheating effects, that term is negligible. So the bare mass
I mean,
is
the
negligible.
original question was that the K is around m phi. And kappa is around 1, over 1. The question is lambda phi not is around m phi or.
I see.
So when you said the momentum is around m phi, so why did you say that?
Could you go to your lattice simulation result, the figure?
Okay. That's the simulation figure.
Simulation figure?
Yeah, the population. Yeah, this one. This one is the lower plus is it is something like the spectrum, right? Our spectra.
Yeah.
And the x-axis is what?
Momentum.
Yeah, in the unit of what? What is the unit?
It's risked by the effect inflaton mass.
Yeah, that is what I'm saying. Why I said that the typical momentum of this particle produced during the preheating would be something similar to the mass scale of inflaton.
The TeV in your example.
Yeah, in this case, he took the M5 to be around TeV. And if we use the unit of this momentum to be the inflaton mass, then this plot means that the momentum, typical momentum of the populated particle would be something similar to the inflaton mass, or 10 times larger, whatever. That's my understanding.
So any reason why it should be around M5?
I think because during the dynamics of preheating, there is just only one time scale. I mean, the oscillation period that is given by the
Okay,
inflaton
okay, good.
mass.
Very good. Okay. Okay, so thank you.
Okay, I think about it more carefully. Thank you for the comment. Okay, this is the end of the first work. So you can obtain some information about reheating from the outcome of lattice simulation in a very simple and minimalistic dark matter model. So the next step is to assume that such renormalizable interactions are negligible. Then the gravitational interaction between inflaton and dark matter can be described by higher dimensional operators, such as graviton exchange and the minimal coupling to gravity and so on. So I think I should go. So I got given 1 hour, right? So I should.
You can go a little bit over. Fine.
So let me go fast. So we want to focus on dimension 6 operators. And in the absence of complete gravity theory, the coefficients are unknown. So the goal of this work is to compute relative size of the different operators. So first, we eliminate two derivative operators by integration by parts. So we are left with these 4 operators, and we try to compute perturbative dark matter production and relative efficiency. And we also compute the equation motion to account for the resonant effect due to Bose-Einstein condensation, as just we did before when we studied Lamé or metrification. And finally, we are going to see if any of these operators can explain the correct dark matter abundance today. So first, we compute all renormalizable by assuming inflaton background as an external source, like this way. And it's more like a QFT exercise. So you can compute a reaction rate or unit volume like this way. And then you want to compare this one with another one, such as O3, by only looking at the difference from the other operator. For instance, this has a derivative squared that corresponds to a product of 2 momenta. So we can read off the difference from the other interaction rate. So in the end, what we found is O4 is a dominant one. As you can see here, so it's much more efficient. And we do the same thing for more higher dimensional operators, such as this. And we found that these types of operators have a suppression factor which corresponds to amplitude of inflaton divided by Planck scale. But this suppression is not small because the inflaton background can have large amplitude. So it means that when you want to study O4, you have to care about other higher dimension operators. Let me skip the second part. So what we found is O4 is the still dominant one, even we study resonant particle production.
What is the O4?
It's here, right? So we do the exactly same thing as we did before. So using this operator, we try to find the signal high h in terms of the outcome of simulation. And this means that even tiny C4 can explain dark matter abundance. It also means that if this is important, the other higher dimension operator would be important as well. So that's it. So we also worked on interesting possibility where inflaton plays the role of dark matter as well. So in this model, inflaton is dark matter. So we try to see if it's viable or not. So we mainly consider non-thermal thermal production. And the point is the universe is already dark in the beginning because inflaton is dark matter. So it's important to explain how inflaton dark matter transfer its energy to the standard mode path. And what we found is, let me skip. It's not easy for the inflaton to transfer its energy to Higgs because in the quantum system they tend to have quasi-equilibrium system. So at most, inflaton should have certain amount of energy of the total system. And in a realistic scenario, it corresponds to 1 over the degrees of freedom, relative standard model degrees of freedom, so which is around 1 over 100. And we found that this fraction is already large. So we end up with too much inflaton dark matter. And so we failed to explain everything. So we found that this non-thermal dark matter is not viable option. So we study a thermal freeze-out dark matter model where dark matter freezes out of the thermal bath. First, we take experimental constraint from this figure, which is combined with the genome one-term experiment and so on. But we found that this lower bound can give huge radiative correction to lambda phi. And this breaks the unitarity condition. So this is not viable. So we have to take another reason where inflaton annihilate to Higgs. So in this case, it doesn't violate the unitarity condition, but it also means that in order for this model to work, the mass of inflaton should be fine-tuned.
What kind of unitarity violation?
So I had to skip because of time. So we also consider the unitarity of the system in the very early universe. So it means that the cutoff scale of lambda in effective scale theory should be larger than typical energy of the system. So around the end of inflation, we can find the potential of the system. like this. And since we have no minimum coupling to gravity, this corresponds to dimension 5 operator that has code of scale, which is 1 over psi phi, the minimum coupling to curvature of phi. And this should be larger than this energy scale, and it gives us upper bound of lambda phi. This is our unitarity consideration. So this case breaks the unitarity, but in this region it doesn't break because of resonant event. So this is the conclusion of this work. And we also worked on another interesting possibility where inflaton first freezes out and decays into dark matter. And we present the result in terms of this R parameter. So if you generate large inflaton, then it should the Bragg ratio of inflaton to dark matter should be small enough to fit the abundance of dark matter. So we have considered different constraints such as normalization, perturbative, and invisible Higgs decay, and so on. So the allowed current space is shown like this. So I think that's it. All right. Here comes the summary. So as we discussed, reheating and preheating is very important. So it is very important to explain how the inflaton field transfers energy to the standard model particles. And based on minimalist approach, we study different dark matter scenarios in terms of inflaton, scalar dark matter, and Higgs. And these are one line takeaway for each paper. Thank you.
Thank you.
Questions?
So could you explain maybe a little bit more the difference between reheating and preheating?
Reheating is more generic terminology to it's a way to reach the thermal universe, while preheating is a very particular reaction that could happen right after inflation. And it's explosive because of the oscillation or inflaton background, and it's large amplitude.
So do you always have preheating or just in specific models?
So you need a coupling to the inflaton to experience preheating effect. So it doesn't always happen.
To do reheating, you also need a coupling to the inflaton, or you don't?
So the
Reheating, just not preheating.
I think it's very little known about reheating in general.
I see.
Okay. Still debatable.
So, I mean, the parameters which involved in reheating are the same parameters that involved in preheating as well. I mean,
So we haven't worked on reheating and microscopic theories of reheating at all. So we don't know.
So I'm saying, let's suppose we have inflaton, and it decays to the standard particles to produce the thermal bath. That is the reheating.
Mm-hmm.
So now, what are the parameters which affect the preheating period?
What are parameters that affect preheating?
Preheating.
Or the interaction between inflaton and other field. I mean, such as quartic coupling. It should be quartic.
Inflaton on the standard model particles.
Yes.
So that is the same interaction which also producing the thermal bath.
Okay, so let me reformulate the question. So let's assume that the inflaton doesn't decay to Higgs. So we don't have a phi hh, but we have phi squared h squared coupling, inducing preheating. So then through the preheating, can you normalize the universe?
That's a really good question. Actually, this is one point of this work. So what we found is it's difficult,
Ah.
as you can see from this figure. So at most, inflat can have fraction of the total energy. So it's really difficult to transfer all the inflat energy to the standard model.
But it doesn't have to transfer all the energy. I mean, the initial universe, I mean,
To
the only
summarize,
condition you can have is reheating should be, I mean, the temperature of the universe larger than MeV is okay, right? Or you mean the remaining energy is too large?
If there is no decay, then it also, I mean, the annihilation also depends on the expansion rate of the universe. So if it's phi square h square, so there is no phi going to hh now. So
Yeah,
phi
I mean,
not decaying.
Yeah, sure. I mean,
So
so
now-
question is,
Yeah, so now this annihilation will depend also on the interaction rate. Sorry, expansion rate. So,
Okay.
so now this, so if this interaction is sufficiently small, so it will stop at some point of time. So in the meantime, whatever standard model particles it will produce, that will be the part. Otherwise, the other part will be frozen as a carbon.
yeah, so,
So that, I mean, then because that coupling is very small, right? So
but can you make it large to produce, things? I mean, so it says it's not possible, why?
yeah, so we try to increase the interaction
Uh,
as much as
Okay.
possible, but still it has the same picture.
so y-axis is what? Energy density?
Yeah, fraction of the energy density for each field.
So
it's-
inflaton energy density remains constant. It can be dark matter or dark energy, I don't know. Why is it problem?
So we want to explain the thermal universe, right?
Yeah, I mean, the upper one is the Higgs energy density, which,
So we are worried if the inflaton has bare mass, it will be the dominant one at late time.
yeah. The fraction is, it's always like that, I mean,
It's like a 80 to 20% because we have
80 to
included
20.
four degrees of
Okay.
heat. So each one has the same amount of
80 to
energy.
20. 1 to 4.
It's because we have included 4 degrees of.
Is the inflaton mass essential?
There is inflaton mass
Essential.
essential. uh,
If you don't have a mass for inflaton, then this slide means something like you can have a sizable amount of dark radiation stuff. No problem at all. If inflaton is massive, then you'd I mean, there would be some problem of overproduction or overclosing the universe. But if inflaton mass is negligible, then it just behave like a dark radiation at the present universe. Then you may not have any problem. Is it possible? I mean, is it consistent with your preheating scenario? When you remove the mass term of inflaton.
Let me think. We have always assumed the bare mass of inflaton our work.
During that period, the inflaton is relativistic, right? density of inflaton.
Yes.
Then it shifts away, and then at some point, due to the bare mass itself, it becomes the inflaton mass is 1 GeV stages. Then maybe so I said there may be some book for it. Maybe some, I don't know. Okay.
Vacuum instability. So sorry, what? F coupling.
Did you consider vacuum stability when you chose parameters? That's the question.
You mean because of this parameter choice or? I see. I mean, it can go negative, so we have to worry about that instability issue. But we just, I mean, for representative values of lambda h, we just take two values. So if it goes negative, we have to be careful.
So in standard model, big stereo coupling is very sensitive to the
Top mass. Yeah. I see. I mean, it has to do with the running of this coupling, right? So we are worried that if it can go negative at higher energy scales. But so in this work, we just we don't just worry about that such complications, let's say. So we just focus on the stable potential of Higgs. We always take positive value of lambda h.
You ask, I should standard model.
Sorry?
Standard model coupling is you ask.
Standard model couplings, yes.
Lambda it is standard model.
It's Higgs self-interaction. So you have lambda h times h to the fourth, right? And this has to do with the stability of the potential because you can go negative at high energy. But we don't just consider such complication in this work.
So another question. What when you consider the minimal coupling for get this?
Do we have in this work, no, but it's also interesting because the non-linear coupling to the dark matter can also generate efficient production of dark matter. So it's also interesting topic. So actually, we are currently working on that possibility.
Draw the line from the bottom. Yeah. So how you mineral operator in this are you? So that's true only when you know renormalize. I'm speaking, I mean, renormalize situation is important that all scales is. For the higher mineral operator, do you assume dimension 4 operator is 0?
Yeah, you assume they are negligible.
But what if you include dimension 4 operator plus dimension 6 operator? then still can we say that higher dimensional dimensions of the break is still important?
I think because of the suppression by Planck scales, I mean, we know renormalizable interactions are always more significant than such higher dimension operators. So, but in the absence of the renormalizable interaction, we have to think about all the other higher dimension operators. I mean, because of the suppression is not significant, I mean, higher and higher dimension operators can be significant as well. So it's really difficult to introduce only one higher dimension operators, not the others. So once your model has a such operator, you need to care about all the other higher dimensional operators.
Understood. I don't know.
But it depends on the size of coupling you choose. Right?
Sure.
For instance, take lambda coupling very small for renormalizable couplings.
But for this work, we assume couplings are similar, so that you can find the relative efficiency of different operators.
You mean for the higher dimensional?
Yes, higher dimension.
But the relevance of a higher dimensional operator is only when you have for example, trans-Planckian inflaton field value, right?
Yes.
That's why you are saying that those operators may be significant.
Yes, that's true.
And it is only about the early stage of preheating.
Yeah. That's a good point.
But then generically, the higher and higher dimensional operator is more important, huh?
Yeah, that's the point of this
Yeah.
work. Yeah. Suppression is not that suppressing.
Oh my God. Yeah, this is the difficulty of inflaton relationship.
Any more questions? Okay, let's, yeah.
So maybe I missed, so when you talked about this thermal dark matter, when the inflaton is itself is a thermal dark matter, in that case, what is the role of preheating? When the dark, inflaton is thermal dark.
That one. So I'm sorry, what's your?
In this case, what is the role of preheating?
So this particular case has nothing to do with preheating. Thank you.
So that one thing is the renormalization scale.
Sorry, with this scale.
Yeah, one. So lambda phi h is the dimension-less coupling, right?
Dimensionless. This is the energy scale of the interaction. Typical energy scale of the interaction. So at the electroweak scale, PV lambda phi h has a lower bound, 0.25, but it's running at high energy at the inflationary scale. It can give huge radiative correction to lambda phi. And this bound breaks the initial condition.
What is the calculation there?
It's an energy scale of inflation.
Over time.
Yeah. Yes. I don't remember, but it has to be the inflation scale. So we worked on the running effect of this bound.
Okay, if there's no more comments or questions, let's thank Jong-Hyun again.
Thank you very much.